So today is a regular lecture, and what I told you last week is this will be given by various people, either some professors from NYU or some specialists in various technical fields. And so that's what happened. Okay, and so today you will be getting a presentation by a specialist in a particular area. And I have to introduce that person. And I'd like to introduce myself. Okay, that's probably the So before we get started on the real part of this presentation is, in the last, now I know you definitely don't fit this category. In the last 110 years, there were 3 major engineering projects undertaken by the United States federal government. These were the largest 3 investments by the federal government in these 3 fields. Any of you have any idea what these 3 different technical investments are? Anybody? Yes? Yes, that's one of them. Okay, we're missing 2 more. Yes?
The atomic bomb project?
Absolutely, that happened during World War II, yes. And we need one more?
The interstate?
No, it's up there, but not quite. No? Yes?
Panama Canal?
What's that?
Panama Canal?
Absolutely. The Panama Canal was finished about 110 years ago, and it really made life much simpler to transport large goods from the East Coast to the West Coast. So for each one of these large projects, the federal government spent a lot of money in order to improve the overall environment for everybody who lives in the United States. Okay? So now we come to what this lecture is all about, and we'll be talking about aerospace a little bit, about Apollo, and we'll talk about LEM. Anybody know what LEM is? Yes? Correct. Okay, we actually have somebody who knew what that was. Okay. And we're going to give you a little bit of an outline of what happened and how this job was done. Because it's important. The reason is not because this happened. How many years ago did this happen? Exactly 50 years ago. So it's our 50th anniversary of landing on the moon. Okay? And the reason we look at that, not because it's 50 years ago, but it's an important technical accomplishment. And it's worthwhile studying the major technical accomplishments, such as the Panama Canal, and the development of the atom bomb, and this, so that we can use that as a guidance for another large project which we will be involved in. So it's a way of learning of what this is all about. So, just a short run-through of what aerospace is. It consists, you deal with vehicles, probes, and systems in aerospace, and that's everywhere. Water, land, air, and space. All engineering disciplines and many non-engineering disciplines. And there are many vendors, and recently this became multinational. Oops. Now, there were major U.S. aerospace players, that's NASA, National Laboratories, Department of Defense, and the major vendors who consolidated about 20 years ago. There were many more of them individuals, such as Lockheed was one, Martin was one, Northrop was one, Grumman was one. They consolidated so that there aren't that many of these aerospace companies anymore. So, this is just a brief history of the space race. What happened is there was a Cold War going on between the Soviet Union and the United States and the Western countries. President Eisenhower said, we will launch a scientific satellite between 57 and 58. Nobody had ever launched a satellite before that. So the Soviet Union launches Sputnik on October 4th, 1957. That's the first satellite ever. So the United States was outclassed in this particular competition, if you want to look at it that way. The United States launched, this was October 57, and in January of 58, the United States launched a satellite. But the difference is, Sputnik was like 86 pounds, the Explorer satellite was like 4 pounds. So yes, we're catching up, but we still have a ways to go. So what happened is, American public opinion was afraid of the United States falling behind. And aerospace endeavors were something where they thought we could really, move ahead on. Looking at the manned space program, in 1961 to 1963 was the Mercury program, which basically dealt with, can you send one human being in space and recover them still alive? Or not too badly damaged, if you want to look at it that way. And from 65 to 66 was the Gemini program, which just follows with 2 astronauts in space. And what the difference there was is they wanted to do space tasks. In other words, can tasks be done in space as opposed to, the first one, which was Mercury, just to get somebody to space and back. From 1968 to 1972 was the Apollo program. And the intent of that program was to take 3 astronauts and take them up and get 1 person or get 2 people on the moon. And we'll talk a little bit more about that. After that, from 1981 on, was the shuttle, which was a reusable spacecraft. All of the spacecraft before, Mercury, Gemini, and Apollo, were basically one-time use and throw away. So the shuttle was the first reusable spacecraft. In '84, the space station was developed, and that basically dealt with long habitation in space, in the weightless area of space, and exposed to all of the radiation and problems or environments that happen in space. From 98 on, the space station became not just American, it became international.
We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other thing. Not because they are easy, but because they are hard. We set sail on this new sea because there is new knowledge to be gained and new rights to be won. And they must be won and used for the progress of all mankind. We shall send to the moon 240,000 miles away, the control station in Houston, a giant rocket more than 300 feet tall, made of new metal alloys, some of which have not yet been invented, capable of standing heat and stresses several times more than have ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communications, food, and survival, on an untried mission to an unknown celestial body. And therefore, as we set sail, we ask God's blessing on the most hazardous and dangerous and greatest adventure on which man has ever embarked. Thank you.
So what you have here is, as with any large project, once it gets launched, it gets started, you have to have somebody who's a champion of this project. In this case, it was the American president, JFK, who said, we will do this, we will get men on the moon, and we will return them this decade. So there was a time limit associated with it. And the problem was to apply Earth engineering concepts to space travel. Nobody had been out in space before, and it wasn't really clear whether the environments in space satisfy all of the conditions that we have on Earth. Like, do the laws of chemistry and physics really work in near-Earth space? And that was not clear. Nobody had ever done this before, so anything was doable. The other thing is looking at it from a different perspective. 90% of the mass of the universe is still unknown today. And that's even known better than when this was started in '68. And the reason is that this is called black matter or dark matter. Nobody knows what it is, but if that isn't there, all of the physics equations of the universe do not work. So we don't know anything about 90% of the universe, and of the 10% which we do know something, we know a little bit of it. It's not really clear whether that 10% is enough to get us going with other things. So the important thing was to try and find out if Earth engineering concepts will work so that everything is proper. Because why should a particular physics, like momentum or inertia or things like that, should that work on the moon or in outer space? Not clear. Unless you actually have proven that, you can't really believe that it will happen. So the first part of the Apollo program was to check out the new space environment. Like robots were sent to the moon and robots were sent into Earth orbit to try and test different things to see how the various equations in mathematics, physics, and chemistry, how all of that fit together. Okay? Now, the other thing is, the whole space environment was different in that you had to deal with a vacuum, you had to deal with weightlessness, you had to deal with incredibly intense radiation, and you had to deal with something that nobody really expected, but probably should have suspected, micrometeorites, like little pieces of sand going at incredibly high speeds, and they'll sort of ruin your day if you just get one of these corns of sand at such a high speed, in your body. That's not good. So you got to find a way of avoiding this. Basic products had to be redesigned so that they would work in outer space. And in other words, how many of you have a watch? Wristwatch. Okay, so that's a sizable number. Okay, in 1968, everybody had a wristwatch. Or today, you don't have a wristwatch, you have a smartphone. Do you think the smartphone is going to survive the weightlessness radiation of space? Nope. It's so strong, the radiation, that you'll just fry your smartphone. And even your watch, because it's made of different metals, they somehow get magnetized differently, and watches do not really work. So one of the things that had to be done, one of the first things that NASA did is they looked at watches and actually gave a contract to Omega, Swiss watch company, and said, we want a watch that will work in outer space and will also work on the moon, because we need some kind of a backup. If we send a rocket up to outer space and to the moon, how do we know that all of the instrumentation is working properly? We want to have a manual way of testing this. So Omega developed this wristwatch, and every astronaut and every cosmonaut, everybody who goes out to space, wears one of these. And this was specifically designed using special materials, realizing that there's a lot of radiation out there, and you want to avoid an impact on your watch functioning through the radiation. What about pens? What would you do in order to write something down if you're in Earth orbit or on the way to the moon? Would your regular ballpoint pen work? It won't work. What would work? What would be a good thing to write things down with? Yes. What? No, actually, that's probably one of the worst things. They tried that, and what happens is, remember, it's weightlessness. You've got this little tip of graphite which will break off. What's going to happen to this little bit? It's going to be floating around the cabin or the spacecraft, and it'll probably go to a place where there's electric circuit or magnetism or whatever, and eventually it'll wind up shorting out some computer systems or radar or something like that. So you want to stay away from anything that's disposable, that has parts that can cause problems by flying around. Any other thoughts of what we could do with a watch? With a pen? Okay, the other thing you could do with a pen is, can we somehow configure a ballpoint pen so that it would work in space? What is missing for the ballpoint pen to work in space? You don't have any gravity, or you don't have a force that really forces out the material which you use to write with the ink, and that's got to be forced out somehow. On Earth, we do it with gravity. in space, you need something to push it out. So NASA gave a contract to the Fisher Pen Company, and they created a ballpoint pen, which basically had a pressurized end at the end of it. So with this pen, you can actually write upside down, which you can't do with a ballpoint pen. You can write underwater, if you're swimming in a pool. I don't know why you'd want to record things while you're swimming in the pool, but you could do that. But in effect, you're floating in Earth orbit in a pool of, total weightlessness. And how do you get this to work? By having this pressurized cartridge, that worked. And even today, you can Google space pen, and for about $10 or $12, you can buy a space pen, which will work the next time you go up to space. It's just a small pen like this, and there's a cartridge in there, and it's pressurized. Okay? You can also, next time you go to the swimming pool, take the pen along and take your notes underwater. Okay, so these are just some of the products that had to be redesigned. There are many other things that had to be looked at also. The cost of the Apollo program was $25 billion. It's about, in today's money, about $150 billion. And comparable to the Panama Canal, which was 110 years ago, or the Manhattan Project, which was the development of the atom bomb. So it was one of the big three. This resulted in 6 successful missions to the moon, and later missions, as the time went on, the rockets to lift everything up were more powerful, and they actually were able to get a lunar rover to the moon. So it's the first SUV that ever drove around on the moon. And also, the other thing about Apollo is, how many of you have seen the movie or heard of Apollo 13? Okay, if you have not seen it, I'd strongly recommend you taking a look at it, because it's a classic case of when you design something and something goes wrong where you haven't planned for it, how do you recover from this bad experience? Okay? Now, when JFK said, we're going to go to the moon, it was not really clear how we would go to the moon. Now, previous things, like Chauvin said, the voyage to the moon, basically shot it up and didn't really explain how you would land on the moon. So the problem is, you really had to leave Earth, and after you leave Earth, you've got to get to the moon. And then once you touch down on the moon, you want to come up again and come back to Earth. So this orbital staging direction was decided upon after about a year after JFK made the decision, we're going to do this. So they looked at what kind of technology is available to get from the Earth to the moon, and they found that getting something into Earth orbit first, and after you have it in Earth orbit, then you fire a rocket and send it all the way to the moon and go into lunar orbit. In lunar orbit, you detach the part of the vehicle that's supposed to land on the moon, while the other part still keeps on circling the moon. And then after the 2 days that the 2 astronauts spent on the moon, they come up again, connect up to the command module, and come back to Earth, and then touch down in the Pacific. So what you have here is you have a coordinate system, which is the center of which is located at the center of gravity between the Earth and the moon. That's why you have it looking like this. This is the same flight profile with a different coordinate system. In other words, here, the Earth everything is with respect to fixed center of mass of the Earth. And if the Earth stands still, what happens is the moon moves in 3, 4, 5 days, how long it takes to get to the moon and back. The moon moves along. So which coordinate system you use depends on what it is that you're trying to prove. And you will find in your future studies that many technical problems get solved by dealing with different types of coordinate systems. So here you're dealing with an Earth-centric, and the other one was, like a center of gravity-centric. These things all had to be looked at and in order to make this doable. The major components of the Apollo project were a command and service module, which basically took 3 astronauts to lunar orbit and back. The lunar module, its only function was, once it was brought to lunar orbit, it goes from lunar orbit to the lunar surface, and the ascent stage, well, it's a lunar module consists of an ascent stage and descent stage. When it touches down, it uses the propulsion and the rockets from the descent stage. After it has done that, in order to go back into lunar orbit, the ascent stage just takes off from on top of the descent stage and goes into lunar orbit. And for all of this, we had a Saturn rocket, which was being developed, so was getting more powerful over the couple of years that Apollo was active, and this was basically the booster to Earth orbit. What did the uppermost part, or that part of it, look like? This part here, going all the way down, is really the Saturn rocket, which was the main vehicle that got all of this stuff into Earth orbit. So once you got all of this stuff into Earth orbit, they were all interconnected. In here, in a shroud, is the lunar module, which is totally inactive from launch until they actually, get to Earth orbit. The command and service module, the 3 astronauts during launch are up in this conical part of the vehicle. This other part of this vehicle is nothing but tanks in order to get from Earth orbit to lunar orbit and back. And this up here would separate at the end and just touch down in the Pacific. One unique thing about this design also had a safety feature, which basically is like a rocket in case something terrible happens, because you're sitting on 1 million pounds of explosives, in effect, when you're at Cape Kennedy. So in order to escape in case something terrible happens, you have this rocket up here, which will take that upper conical part where the 3 astronauts are during launch and take them away, so it's like a jet fighter, a pilot who ejects from his jet in order to get away from a dangerous situation. So this upper part, but luckily, this upper portion here never ever had to be used. What happens here is, this all is in Earth orbit, and I will follow up with the comparison. The command and service module can hold 3 astronauts. Oh, by the way, this presentation exists on the EG website. So whatever I'm saying, or any pictures you see here will be there, so you'll be able to take a look at it again. The command and service module will hold 3 astronauts, which are up here in this conical part. This down here is nothing but tanks. This is nothing but tanks and 1 large rocket engine. The lunar module can only hold 2 astronauts. Was specifically designed for that. And it was basically, it's got the bottom part here is the descent stage, and this is the upper part, which is the ascent stage. It goes down on the moon with both the ascent stage and descent stage. The descent stage basically firing its rockets in order to brake it so it comes down to a smooth landing. After the landing and the moon mission is complete by the astronauts, they will then go in here into the ascent stage, and only this part of the ascent stage will go up to lunar orbit to rendezvous with the command and service module. So there's a docking feature where this part here can dock to the top of the lunar module. Oops. The lunar module was by far the most complicated vehicle that was used in the Apollo program. The other mission portions were very clear what they had to do and what they didn't have to do. This was basically getting the astronauts to the moon surface and and after using up the descent stage, they used that part of it to get back up into lunar orbit. Also, there were lots of computers, radar, and anything else that was necessary. This was the rocket. Up on top This is where the lunar module is in here, the shroud. And above that is the command and service module and that rocket, which was the safety escape portion.
Precisely directed, know that we're on course, first of all, for Earth orbit, and precisely inserted onto the right orbit, right trajectory for rendezvous with the Moon.
Paul of Houston, you're right smack dab on the trajectory. You're doing a beautiful job. I got a yellow program. Trajectory's good. Thrust is good. Right away, Houston.
At last, I'm leaving Europe, and I'm destined for the Moon.
What a ride, what a ride. Roger, we copy, Pete. That looks good up here, too. Roll complete. Really a rock and roll ride.
You can feel it shake. There's a real strong vibration. Of course, you're up at the end of this beauty. Here you are going along with the G on you. It's up to about 4 Gs, but you're psyched up, good shape and all that. Even lifting your arm to move switches, no problem.
Well, you are go for staging.
Here you are coming up on stage, and when staging happens, it's like, man.
So when was brought into Earth orbit, this is the bottom, or the top part of these S4Bs of the Saturn rocket. Here in the shroud is the lunar module, and this is the command and service module. This is where the 3 astronauts are, and this is where tanks are in order to use, so that when this thing separates and turns around, it has energy for this large rocket engine.
There's nothing startling to report about the run. There's a whole lot. No, there's nothing really spectacular different to report on the ride. We'll hold off one end.
Okay, there's nothing special there. Okay, so what happened in this translunar situation is the entire vehicle, or the upper part of the vehicle, went into Earth orbit. Once it was in Earth orbit, the command and service module pulled out, turned around, and docked with the lunar module. It then took the lunar module, and here it's connected to the lunar module, and going a little bit further away, it takes an evasive maneuver so that it stays away from all of the other stuff that is up in Earth orbit because of this launch.
Paul, this is Houston. Your goal for LOI. You are Houston. Jim, you want to go for the burn. Go for the burn. Okay, Paul, go.
You're going too fast to orbit the Moon. You're rocking on ready.
Wait 2 minutes, man. Give it a final trim. Third time is 15 seconds, so it's going to go in a hurry.
You're in the burn position. You're ready to go.
Maybe let's make this one.
Then you look, and there it is.
35 seconds.
It's 2001 type stuff. That old moon's just growing magnificently fast, and it's just filling up that hatch window, and you're drifting into the shadow.
Hey, baby. Hey, Perform flight command module. Next we hear from them. The lunar module should be undocked from the command and service module.
They're in lunar orbit now, and the lunar module has been manned by two of the astronauts.
They just say kids, but there ain't nobody in here but one guy. Don't get lonesome out there, John.
I wish I could go down there with them. You may not talk about it very much, but part of your training is coming back by yourself.
This is the astronaut who stays behind in the command and service module, where the other two are the lunar module going down to the moon.
Wish the damn thing could hold 3 people.
So this is the lunar module flying in lunar orbit by itself. And here's a picture of the lunar module. These are 4 legs, and there's also a sensor stick that sticks out in case they touch down on the lunar soil, so that the engine shuts off properly. They had also had 2 or 3 other systems in order to shut the engine off, but mechanical sometimes works best compared to other systems.
The vehicle is surprisingly free of any debris moving around. It's very clean. Roger.
When they mean it's surprisingly clean,
It's pretty hard to describe this view. It's really great.
during construction, lots of little pieces can be left over and they fly around, and that really causes problems. So here you've got the command and service module pushing the lunar module into lunar orbit. Here they separate command and service module with 1 astronaut left up here and the other 2 astronauts in here. That's why he's saying it's really lonely up here for only one of them in here. This is where they touch down, and these are the first steps on the moon.
Econ, Sergeant, go. Final, go. Guys, go. Patrol, go. Telcom, go. GNC, go. Capcom, we're go for landing. Eagle, Houston, here, go for landing, over. Okay, Houston, we'll give you a countdown. 4, 3, 2, 1, fire. Oh, baby. Hey, you're coming down to that ground. Look at that drill. That's gotta be probably Diamondback right there.
When the picture's over, you get your first look, it was nothing but 9 million craters after a terrible sinking feeling. Obviously, you didn't recognize a thing after studying all these photographs. Nothing looked right.
How you doing, Control? Where's that good? You're fine. How about you, Telcom? Go. Guys, Chevy. Go. Final. Go. You're a go. You go to continue power and descent. You're a go to continue power and descent. Roger.
All during this power descent, I kept telling myself, Jim, this is not for real. You're back in the stimulator. Just remember that.
Eagle, Houston, it's descent to the fuel. To monitor, over. Eagle, Houston, everything's looking good here, over. Houston, I'm getting a little fluctuation in the AC voltage down. Roger. Stand by. Looking good, you're still looking good. Houston, you're looking at our Delta H. That's affirmative. Looking good to us, over. Eagle, Houston, we'll monitor your Delta H here. 6.25, throttle down. 6.25, throttle down. Roger, copy. 6.25. Let me try it on again now, see what happens. We got data drop out front, stand by. We're going that line. If it does 3 o'clock, we'll be good. We're going that alarm. I heard it there, go for that. Roger, we got good data. Altitude, velocity light. Eagle, we got you now, it's looking good, over. 4 forward, drifting to the right level. Coming down to 20 degrees, 21 down, 33 degrees. Window, 35, window. Picking up some dust. And a couple of big boulders. Coming right, got a good spot. Not too bad. There comes the shadow. Oh, are we coming in?
These are shadows of the legs while it's landing.
Everybody stuck down. Stand by. Bam. Listen, Tranquility Base here. The Eagle has landed.
So at this point, we go a little bit into the design of the mission and the hardware. This is really where we can learn from. You're not going to be designing something that goes to the moon, but if you're designing something comparably in difficulty, this is what you have to do. Notice that this is an iterative design. When it first started, nobody knew how to get from the Earth to the moon, shoot directly, or some flyby or some other things. With time, they found out that the best way of doing that was using the gravitational pull of the Earth orbit and the lunar orbit in order to get there. The other thing is, this was multidisciplinary. You're not dealing with just one discipline, say mechanical engineering or chemical engineering or electrical engineering. They all contributed to this. This was the first really major project where different disciplines sat around a large table and they said, okay, we should do this, and somebody over here says, no, because of library restrictions, you can't do that. So this is really important, this whole multidisciplinary approach. This is something which we're also trying to do in this course, so that when you're working on a semester-long project, you will look at it from different perspectives. There were many contractors and subcontractors, and NASA was the coordinator and the project scheduler. You will be, for your semester-long project, you will be using a program called Microsoft Project. How many of you are familiar with it? Okay, just a couple of you. This was developed because of the Apollo program, because in order to keep track of many different tasks, it was necessary to coordinate that all on a computer. So what were the priorities for the lunar module design? Well, JFK said it will happen. We've got this. It has to perform. It has to work. The schedule is at the end of the decade. Cost was really minor when you're falling behind your major competitor on something this critical. You've got to try everything in order to get back up to speed. And the important thing was obviously to minimize weight. Every pound that you wanted to bring back from the moon required 4 pounds of launch weight. So it made everything that you brought back from the moon weighed much, much more in the original design of the rocket. The lunar module design was designed and built by Grumman on Long Island. It was tested and used in a very large vacuum chamber. Because keep in mind, this would only work in the vacuum of space. It would not work in a regular atmosphere. So it was necessary to have a very large vacuum chamber to put the lunar module in there. And also to test it and to have 2 astronauts in there so that everything that astronauts had to do would work. So the lunar module was active in lunar orbit, lunar landing, lunar ascent stage, lunar ascent, and lunar orbit. The ascent station, destation, these were not tiny. They were about 10,000 pounds and 20,000 pounds each. Okay, the lunar module, first design, was like this. It had 6 legs and had, like curved surfaces. And it went over until the final design where it had 4 legs and every surface was flat. Now, how could you get away with having flat surfaces as opposed to having all of these nice curved surfaces? Why do you need curved surfaces? Remember, the people who designed this were engineers. and they were aerospace engineers. What did aerospace engineers design? They designed planes. And when you design planes in the Earth atmosphere, you've got to have smooth surfaces or the plane won't fly right. So they were preconditioned. If we're going to build another vehicle, it's going to have, round surfaces. Turns out that because everything is being done in the vacuum of space, it doesn't matter if you've got these round surfaces or if all of these surfaces are flat, because it's within a shroud when it gets lifted off anyway. So it doesn't really matter that you have an aerodynamic design. So it's a totally new way of thinking at it based on the requirements of what you have to do. Oops. Okay, in 1960s, the technology, if you look at it from today's perspective, it wasn't much to brag about. There were no satellites. There were ground stations. So whenever you finally had a satellite that actually went around, when it went over the Pacific, you had about a 45-minute period of silence. You had no idea what was going on, like in the satellite. Slide rules were used. There were no calculators. And it's amazing what you can do with slide rules if you don't have a calculator. And there were no calculators then. Computers were monstrous. The most expensive part was memory, so 32K of memory, and everything was done with card input. There were no tapes, and there was no magnetic way of inputting information. It cost $500 an hour in order to run these large computers. For $500 today, you can buy a laptop that has more power than these huge computers at that time when the Apollo program was conceived. There was no software at the time. You had to write your own engineering codes. In other words, they provided you with a computer, but if you didn't write in machine language and you interface with special hardware, it wouldn't work. Limited copying was done on thermal paper. If you exposed that to sunlight, it very quickly would yellow out and couldn't use it anymore. However, the wheel, the pencil, and the phone had been invented, so it wasn't totally Stone Age. Okay, what was my contribution to this? Well, I was responsible for the web thermal analysis. And the date of this is 31 January 1969. Anybody know when the lunar module, when man first landed on the moon? July 20th, 1969. So this is from January until July. And what this is a final pre-flight mission analysis of all temperature components of the lunar module. In other words, I was responsible for everything dealing with temperature. And he wanted to be very sure that everything worked in the proper range. When you buy a computer, when you buy a radar unit or anything, they all have temperature limits. It's got to be between, say, like 50 degrees and 70 degrees or something like that. When you've got astronauts, they have temperature limits. You don't want to freeze them, and you don't want to boil them either. So you've got to be careful about anything that is inside the lunar module, that it's all within the proper temperature range. What this is basically, this says, this was the thermal analysis number 6, and dealing with both hot case and cold case conditions. So in other words, once you shoot off the whole rocket with all of the contents, including the lunar module, you have very little that you can do to control it. You can rotate it and turn on a couple of heaters, but you usually don't have enough energy to do much with it. So the important thing was to find out exactly what could be done, and this was the final pre-flight analysis. This basically says everything was within acceptable limits. This, by the way, is also, when you look at it on your website, there are some constraints for the lunar module mission, and then primarily had to deal with the orientation. The sun is very, very bright. The site that gets exposed to the sun broils it or brings it up to 350 degrees. The side on the other side of the lunar module, or whatever you have in space, is at minus 460, which is absolute zero. So you've got to be careful. You can only expose something for a limited amount of time to the sun, both for not overheating and also not for overcooling, because on the other side of the heated side is the shadow side, and that's close to absolute zero. So anyway, this is the thermal analysis number 6. Why was this thermal analysis? And this was myself responsible for this. Why was it analysis number 6? Did I mess up the first 5 times? I hear some laughs going on. Well, to reassure you, well, the lunar mission did succeed, and I didn't mess up. But the reason this is number 6 is this is what happens in every large project. When you have a very large project, you can't finish everything and say this is it. You basically do as much as you can, and then you freeze that design. That's design number 1. And every technical discipline does an analysis of what is going on in that particular environment. After that, changes are made to the design to make it better. That becomes now design number 2. That requires an analysis of all of the technical disciplines for structure, for propulsion, for center of gravity. All of these areas have to look at what is important. So this basically means there were 6 major designs of the lunar module before it was finally released in order to go into the actual mission. When you deal with thermal analysis of space, space is very hostile. It goes from minus 460 Fahrenheit, that's absolute zero, to 350 degrees F when you're totally facing the sun. And heat transfer modes are normally conduction, convection, and mass transfer, and radiation. On Earth, it's usually the first 3. In space, it's primarily radiation. So you have to really look at how everything is in order for it to work properly. Okay, in order to protect the lunar module with the proper temperature, the lunar module had to be insulated, special insulation had to be developed, peak thermal loads, like when the rocket engine is firing, when every electronic piece is on, there's tremendous heat load, and you want to make sure that the astronauts stay comfortable in this. So you want to keep a 40 to 80 degree environment, and there should be no condensation. This is the lunar module as on the moon. One of the astronauts here, they have a bay here where they had experiments stowed. Also what happened is, if you look at this, this is very thin aluminum metal, which is the shroud for the lunar module. Also here. The reason for that is, I mentioned the tiny sand particles which are traveling at very, very high speeds. This is necessary for the ascent stage to survive. Descent stage isn't exposed long enough for it to matter. Okay, so in order to do a thermal analysis, a computer model had to be built. This model had to be tested in a physical test and in the first flight, and different missions, hot case, cold case, all had to be looked at. You had to look for out of design conditions. Look for something that you didn't really expect. Why is this getting too warm? Why is this getting too cold? How do we prevent that? So we calculated the transient temperature history for all nodes. We had about 790 points for the ascent stage, for which we calculated the temperature, or the average temperature. And the descent stage had 500 nodes. And it took 1.5 hours of computer time for a 150-hour mission. And this was all submitted in 10 boxes of cards, so it's 20,000 cards. A card is like the size of a dollar bill. There was no way, nobody would read it. There was no magnetic way of entering the information. Only near the end of the Apollo program did they finally get like 2-inch wide magnetic tapes in order to store information, both for input and for output. Oops. This is the lunar module with all of the various components. There are, for instance, like here, there are clusters of 4 mini rockets here, on all 4 sides, because once you're flying, how do you orient this? By just having one large rocket at the bottom of this, you can't really do it. So you need all of that. You have many antennas, lots of electronic stuff that all has to be looked at. These were the major nodes that we calculated the temperature for. This was structure, was the type of aluminum in order for that. This was for the acid stage. And for the descent stage, we also calculated all of these things. These all had to be calculated to find out, is there some area in the air that is too hot or too cold, which would cause the flight to fail. Heat transfer equations were solved through numerical methods. Solution time steps were about 60 seconds in order to get a stable solution. And there were separate detailed analysis of critical components. And there was a special cooling loop for instruments and electrical equipment. There were special problems with radiation heat transfer, complex geometry, and view factors. In other words, even if something faced this way and this way, there was still radiation. Some radiation from here went to there, so there was always some kind of a coupling. And that had to be all taken into account. Many variables had to be looked at, hot and cold cases, different orbits. For instance, if you're going in an Earth orbit, and you're with a lunar module or with a satellite, which is colder, a polar orbit or an equatorial orbit? Which one? Nope, actually not. When you have an equatorial orbit, you continuously go around until, like, you average out things. With the polar orbit, you can set it up in such a way that either you've got continuous sunlight all the time, or you only have it for part of the time. So you can really, based on your orientation, you can really vary that. Okay?
This thing came to a stop on the moon. There was kind of a letdown saying, you know, we're going to have to get it going fast again to get back home.
Good luck, Charlie. Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his finding. Don't run into our home.
And here's the SUV on the lunar surface. Okay, we now have the lunar module, and the acid stage will be taking off, connect up to the command and service module. This gets, the lunar module gets jettisoned or jumped. This part of it goes to Earth orbit.
Roger, understand. We're number one on the runway.
They're number one on the runway.
The moon is different. It's become man's first outpost, our first footstep in space, where man was able to look back at the Earth and see the Earth and see himself in a different perspective.
5, 4, 3, 2, 1. Ignition.
Descent stage behind, ascent stage takes off with the astronauts. So now the lunar module approaches the command and service module so that they will achieve the transfer of the astronauts back to the command and service module. And the remaining part of the lung gets scrapped. So what happened is, conclusions, the model, the thermal model that we built of vacuum chamber test results, we matched that. the flight data verified the correctness of the model. And so basically, land thermal analysis is one discipline that provided engineering support for this multidisciplinary effort. Command and service module takes off from lunar surface, a lunar orbit, comes to the Pacific, comes down with parachutes, and gets picked up by helicopters. So what can we say from this? Apollo was a success. Many technical things today derive from Project Apollo, and American technical leadership is directly a result of many developments started when you are under adverse environments and you really have to make sure that things do well.
Feeling a bit proud of the trip, but still happy to be going back home and back to our home port.
We set sail on this new sea because there is new knowledge to be gained and new rights to be won, and they must be won and used for the progress of all mankind.
Okay. And just to prove that I actually did get involved, that's to give me a certificate that I really worked on that.